research associate at the Montreal laboratory at Ecole Polytechnique in Montreal. I'm working mostly on Trace Compass, and I'm the one responsible for making sure that all the students' contribution make it to the end of the end users. So today I'll be presenting how we've used the Trace Compass traces to model and analyze and extract performance data from a multi-threaded application that is Trace Compass. So, for background, Trace Compass analyzes a huge amount of trace data. And while it scales pretty well for most cases, it happens that a trace comes and Trace Compass is just not responsive. The user will complain that the GUI is frozen, that Trace Compass is slow. Well, we're not perfect, but we would like Matthew to brag that he's a contributor to the single greatest software. So we're trying to improve Trace Compass. So how do we do that? We look at the faulty traces. We try to improve. We know that there's problems in the backend with those traces. We propose solutions to the backend, and then we put them into review, and there comes a review hammer. Okay, so we have a backend that is pretty stable. Now you're making changes to the backend to improve performances of the worst case, but does it really affect what we want to improve is the user interface, the user experience. Does this patch really improve the user experience? Well, obviously, if you have 50% improvement to the front end, it will trickle down in the back end, it will trickle down to the front end, right? You're sure? So the burden is on us to prove that this patch actually improved the front end. But one does not simply benchmark a user interface. Okay.
Press F5.
That's 5, so that's okay. So we don't simply benchmark a UI. I've heard Java described as a big pile of threads, and that is right. And every single one of those threads has an impact on the UI. We have one UI thread that is running, and that is being sent tasks to run on it, and from the different other threads. So whenever one of those tasks takes too long to run, we will experience a freeze of the user interface. And we also have the different views of the UI. Each view will spawn a thread in response to a user action for zooming and for building data, and at the end it will send a request for refresh to the UI thread. But whenever one of those threads takes too long to send a refresh request, then the user will experience slowness. It will say that the UI does not answer very rapidly. So what we want to benchmark is not really, it's not just putting a timestamp here, timestamp there, making a difference and printing that. It's all this interaction that we have to model somehow and extract performance data from it. So how do we do that? We could use a profiler. That's easy. There's a lot of Java profilers around. We just need to plug it and start profiling. It will take generic sampling data at different times. It requires no knowledge of the application. But what we get in return is an aggregated data of which functions took more time, which objects took more memory, but it won't tell us why these methods were called, why those threads were spawned, with what parameters. It may help, but it may also mislead when you use only the profiling data. And also for small functions, you may totally miss those calls because they're not often. If you provide too much, then you impact the performance of the UI that you want to benchmark. If you provide too little, then you miss some stuff. So what we really want to do is to be able to exactly measure some part of the code, and other parts we don't care about, at least not yet. So that is exactly what tracing is. But Trace Compass as an application is not yet, was not fully implemented before this. We couldn't, so we had to decide how to instrument trace compass. It's a Java application, so there's a few Java frameworks available for tracing, what is called logging in Java. For example, GUI, the Java utility plugin. This is what we will be using. This requires a knowledge of the application. We can put the log points at very specific places, like the start and end of the threads that impact the user interface, the backend query, for instance, and we can log any other interesting event that's happening in the UI. So now that we have an instrumented application, we first want to know what is the cost of tracing it. So we did a few benchmarks on that. It's near zero when the log points are disabled, which is what is expected with tracing. You don't want the instrumentation to take away some performances. But each trace point has each GUI log point has an order of magnitude. So there's overhead that depends on the tracing level, the number of log points. So as a rule, we want that the normal level of tracing should have the least overhead when it's enabled in the large when running, so that we can extract performance data from them. And we also have a lower level of tracing when we want to really debug or fine-grain the applications. And then with the logging, we need to handle those log data. There's a few options like a file handler, but that's only good with the single threaded. If you have many threads, the file becomes a bottleneck. So LTTNG has a GUI agent that can be used. So that's what we will be using because it has a very good multi-threaded performances. So now we have an instrumented application. We can run it with LTTNG. What do we get? We get a USD trace, where each log message that we put on the GUI log point becomes one field of an event. That's not good enough for us to work with, so we did a new trace type for it, because all the logs, we had a certain format, so we parse it, and like what's in square bracket becomes the event name. And then we have a comma-separated string of field equal value, so we add that as field of the event. And now we can use that with data-driven analysis, with an XML analysis. And then we can do whatever we want with the data for further analysis. For what we will be doing, that is benchmarking the user interface. We will take the data, the different threads. We have a trace point at the beginning and the end of the function. So we will take that and the points of the backend, and we will make a call stack out of it. Because after all, it's a stack of executions of threads. So we're not interested in this case with the actual thread ID. We're more interested in the views and traces, because different traces will have different behavior. So we will separate our data in the trace view way. So what we see here is a call stack where we have one trace that is called many threads full. We separated the first two call stacks are call stack usual of the threads, and we have also the UI threads that were involved in this trace view. At the very bottom, we have the results of just the UI thread, what executions were done by the UI thread itself only. And once we have call stacks, there's a few analyses that can be done with it. For instance, we can have flame graphs. And the flame graphs will give us which which threads took more time for the different traces. So here we have for the resources view and the control flow view. So we see that there's a lot in the control flow view, the refresh, the UI thread, there's a lot of refreshes that are done. And what's interesting to see here, though, is at the top, we have what's taking the most time on the UI thread itself is the CPU usage viewer, which is supposed to be oh, by the way, we have this data view. It's not one of the main view, but it's actually the one that takes the most time on the UI. So why is that? It was a bit surprising. So we went into the code and realized that actually we would go to get the data directly from the UI thread instead of getting it from a different thread and just calling a refresh on the UI thread. So that's this means that the user will experience a little freezing with that view, maybe because it takes more time. So that's something that we can improve right away and easily without going into the backend yet.
Did I get you right that the main function is written inside this?
The name of the function or the instrumentation is written in the, because I can't read it.
Yes, inside is the name of the function, like what we have here is time graph view refresh start. Because that's the name of the function that started this. Okay, the first two views I showed were done only with an XML data-driven analysis. This one here required a bit of coding, but hopefully it will be made generic soon and it can be used by other analysis. So again, it's the data from the plane graph, but in a statistical view. So here we see like a control flow view. We have the average time each method took, the number of times it was called, total time. And what we have also for every child call is the average number of children called per call of the parent and the total time, the time of those children in one call of the parent. So we can compare the time, the per call time with the average time to tell us, to give us an idea of how much time was spent, the percentage of time that was spent in the child. So like here, 2.6 seconds in full query on 3.7 seconds of the parent thread. Also what we have extra data that we can get for the cache hit and cache misses. This is data that we get from the backend. We read nodes on disk in the backend, and sometimes they are cached. When we need to read them, they are cached, so we can get them from the cache. And a cache miss means that it was actually read from disk. So in those cases, we see that we have a good percentage of cache hits. So the disk is probably not a bottleneck in those cases. And the next column is the time for the first refresh of the view. At the first time, the thread called for a refresh. So this means that, like here, the Zoom thread, there was nothing to be seen by the user for 4 seconds. Like between the time he asked for a refresh of the view and the time it was actually refreshed, there was 4 seconds. So this is all data that we get from the GUI trace that can help us improve, get some idea of what's going on in our application. Another thing that we can do with LTTNG trace data is to correlate it with the kernel data. If we take a kernel trace at the same time that we're taking the GUI trace, we can know what's going on a bit more. For instance, we can do the critical path. This screenshot here is the critical path of the build thread of a trace that wasn't cached before. So what we see, the process at the top, was the build thread, and it depends, there's a lot of arrows there, a lot of Java processes, so it's a bit difficult to make sense out of it since we don't know what was running on those other Java processes. I guess we would need more instrumentation. We can also correlate, we could say, okay, we know that on this thread was an event request, we could add this information to the critical path, but we're not there yet. And what we see here is that the purple color is waiting for the disk. So it's actually waiting for the disk, which is normal since the data was in cache. So it's getting reading from the disk. Another thing we can get from a kernel trace is we saw the call stack earlier. We know when it starts, when it ends, but how much of that time is actually spent on the CPU. The run we've made, there's two cases. The many threads trace, the control flow view, is when only the control flow view is open, and the many threads full is the same trace, but when all the views are open. So there's more threads that will be spawned. So what we see is in the case of only the control flow view open, the duration is pretty much the same as the average CPU time, which is good. In the other case, the average CPU time is much lower than the average duration. There's almost 1 second difference. So, well, that's to be expected, especially when we see all the threads that are involved with a single thread. Well, they all compete for the CPU. So, of course, it will take more time, but that also means that the user will see more, will wait more for feedback. And when we know how the user uses trace canvas, he will usually open a view, then another view, then go to another view, and one view will be hidden behind the other. But they all try to update at the same time, even though that are hidden behind. So at one point, even though the user only sees 3 views, there are 6 views trying to update, then you will see a slowdown. So that can be also a way to improve, to just update with higher priority the views that are visible instead of just updating them all with the same priority. That will improve the responsiveness as we do more analysis.
Good question. For the flame graph that you've shown on the previous slide, so typically flame graph is more a weighted amount of time spent per, let's say, function. So when the width of each function is weighted, if you can go back to one slide. So what are the so what are the seconds there? I mean, is it a timeline? I mean, is it really a flame graph, or should it be rebranded to something else?
It's a flame graph.
It's really
the duration. Duration, not weighted on the number of calls, but weighted on the duration.
It's like Chrome is saying it's flame chart. That's what they started calling. Chrome has something going down there. Just like Chrome.
So yeah, in conclusion, we have some steps to improve the performance for the user. As I showed, the XY viewer should compute the data in the white thread, and the views in general only update the visible one. But most importantly, with this work, we actually have some metrics to compare run. If we run the same, we run the visibility bot that will do the same user events on the different traces, then we can try with different batches sets, and we can compare the results like that. So we can know exactly how it improves. So I don't think I have time for the demo. So I will just review with the resources I used for this presentation. There's the experimental RCP that has all this available. The GUI feature is on the separate update site, and I have a few example traces that I used for the. Thank you.
Any questions? Yes.
Hey, you have an example there where you correlate the kernel events with the user space event. And in my company, we find that this is a hard problem because we have to synchronize timestamps. Timestamps living in the kernel compared with timestamps available in user space, especially JVM, which does not allow you to get more than millisecond granularity until Java 8, I think. Java 8 includes it. It does not have the time. That's not a real nanosecond time. that's Simpson clock, which is the beginning of the JVM. So it's not the real time that you will get. So how do you manage to correlate it?
Actually, for the Java trace, you mean?
Yeah.
Actually, it's with the TTNG UST. That's why we use this handler, because it has the timestamp in nanoseconds.
How do you get it?
Clock get time, clock on a time.
Oh, so you make a GUI call?
Yep. So all the UST tracing is really done from a JNI. So all the buffer handling and rendering that buffer, as well as reading the time and getting the current CPU number, that we're already at native code level.
Yeah, and I checked like the millisecond time because the log record has a timestamp per millisecond and the TNG is a nanosecond. And it's within the same nanosecond most of the time. A millisecond, yeah.
Yeah, but you cannot.
And you cannot use the Java timestamp to correlate with the kernel. They use the timestamp taken by the user space tracer to correlate with the kernel timestamp. Another question?
Everyone wants to leave for lunch, I guess. So we have to be back here at 2:30. There's Jan and Lode from Google who will present their